A comprehensive analysis on aerodynamic characteristics of a MPV spoiler. Abstract, performance, handling, safety, and comfort of a car are significantly affected by its aerodynamic properties. Getting immense power directly from the engine is just not enough to evaluate the performance of the car. Aerodynamic properties must be considered too by analyzing the lift, drag and stability performance of a car. In order to improve a car's aerodynamic properties, aerodynamic features such as the car design itself, rear spoilers, diffuser kits, vortex generators must be taken into account. Rear spoiler acts as an accessory that functions to impair any unintended airflow across the vehicle or in scientific terms, to spoil the laminar flow of the car's aerodynamic movement and motion. This rear placing device creates an area of high pressure to replace the usual low pressure over the trunk, resulting in increasing stability of the car. Basically, rear spoilers are fitted at the trunk of a sedan car for its performance, but does it render the exact outcome if a spoiler were fitted in a larger vehicle such as the multi-purpose vehicle, MPV? Or just for the sake of styling purpose? Thus, this analysis is regarding the effect of rear spoiler on an MPV, and the objective of this study is to investigate the aerodynamic characteristic on an MPV vehicle with rear spoiler using CFD software, namely, ANSI. A simple model of the MPV had been drawn using Kasia software, imported to ANSI software and ultimately to operate the aerodynamic simulation. Keywords: vehicle aerodynamic, MPV, spoiler, drag force, lift force, ANSI simulation. Introduction. Nowadays, the normal sedan vehicle including multi-purpose vehicle, MPV, are customized to become sportier and add some wow factor to their ordinary vehicle by the respective owners for multiple reasons. Having outstanding power from the engine leads to immense speeds for which the aerodynamics properties of the MPV by original manufacturer are not sufficient to endeavor desired downforce and handling. The safety, comfort, performance, and handling of a vehicle are significantly influenced by the aerodynamic properties too. Additional fittings are mounted to the body such as rear spoilers, vortex generators, air dams, front and rear bumpers, diffusers, and many more to channel the airflow in various oriented way and offer greater reduction to drag and enhance the stability. Basically, aerodynamic properties on a vehicle's design is the paramount demeanor of a vehicle's design is to harvest steep complexity phenomenon, one which encompassing an artful iteration and integration of advanced engineering, technology, and design aesthetics. Paramount emphasis focused on the aerodynamic properties of any vehicle to design as an aerodynamically well-engineered vehicle employs the least force and overwhelm the drag exerted by air and hence flaunts higher performance, cruises faster on lesser fuel consumption. 3. Aside from improvised fuel efficiency, an aerodynamically superior vehicle offers greater handling and stability at respective speed and also minimize unintended interactions on roadways with other vehicles. 2. Aerodynamics. Aerodynamics in general is a part of fluid mechanics which focuses on forces generated on a body in a flow and involves a lot of calculation in vast properties of the flow such as temperature, pressure, velocity, time, and density. In order to calculate the type of forces and moments acting on the bodies, one must first discern the pattern of the flows. 5. Automotive aerodynamics is a type of analysis of the indicative road vehicles involving related properties such as reducing the lift and drag force at high speed and preventing the irregular wind sound. It is also required to produce downforce to improvise cornering and traction of a vehicle. Obviously, the vehicle shape does give response on the aerodynamics characteristic. 3. Rear spoiler. Rear spoiler is an accessory to escalate downforce for vehicle mainly on a passenger car. It is an aerodynamic accessory that designed to tarnish any unfavorable airstream across a car. The concentration point is at the rear region, depends on the shape of the rear region, either the MPV's is fastback, square back or notchback because not all spoiler can be mounted at any type of MPV. Rear spoiler contributes some major aerodynamics force factors which are lift and drag. The contraction of drag force can save fuel, moreover, spoiler can also be used to control cornering and stability in motion. 6. Besides that, it even functions to reduce drag and rear axle upsurge. Proton XORA. 4. Drag force. An aerodynamic drag force is the force which opposes the forward motion of the vehicle while in cruise mode and acts externally on the body of the vehicle. The drag force can be measured directly by simply rendering the body subject to analysis of fluid flow, through detailed calibration and measurement of the displacement towards the flow direction. Drag force is usually an undesirable reaction, like friction, and most scientists and engineers are trying to minimize by creating alternatives. Reduction of drag is closely associated with fuel efficiency in land, sea, and air transport with improved durability and safety of structures subject to high winds, vibration and noise reduction. 7. More sophisticated drag measuring tools named drag balances uses flexible beams fitted with strain gauges to calculate the drag electronically. Besides that, it can be calculated using the formula, 1, as shown below. DA equals 1/2. V2 CDA, 1. Where, CD equals coefficient of drag. Equals density of air kg/m3. A equals frontal area, m2. V equals velocity of vehicle m/s. The drag and lift forces depend on the density of the upstream velocity of the wind, air, the upstream velocity of the wind, and the particulars of the body are among other elements which need to be taken into consideration. Therefore, it is convenient to conduct with appropriate dimensionless numbers that represents both the lift and drag characteristic of the body called the drag coefficient. Modern road vehicles such as cars have the value of coefficient of drag, CD from 0.2 to 0.48. The smaller the value of CD, the better the aerodynamic flow of the vehicle. In general, the blunter the vehicle, the higher the drag coefficient. As a result, the percentage of fuel efficiency due to reduced drag is about half the percentage of drag reduction at highway speeds at 110 km/h. 9. V. Lift force. The aerodynamic lift force acts vertically to the vehicle body that is perpendicular to the airstream direction. Lift force also generates undesirable impact to the vehicle as it greatly diminishes frictional forces between the asphalt and tire of the vehicle and dramatically changes the handling characteristic of a vehicle. The lift force can be calculated using the formula, 2, as shown below. LA equals 1/2. V2 CLA, 2. Where, CL equals coefficient of lift. Equals density of air kg/m3. A equals frontal area, m2. V equals velocity of vehicle m/s. Some accessories such as the spoilers and inverted airfoils on vehicles are created for the purpose of avoiding lift or even generating negative lift to improvise control and traction of the vehicle. Some early race cars actually took off at high speeds as a result of the lift generated, which alerted the engineers to come up with solution on ways to greatly reduce lift in future design. 8. 6. Laminar and turbulent flow. For instance, being around smokers, it is discerning that the cigarette smoke afloat in a smooth plume for the first few seconds and starts fluctuating randomly in all directions as it continues to rise. Likewise, a careful inspection of an airflow reveals that the flow is streamlined at low velocity but turns chaotic as the velocity increased above a critical value as shown in figure 3 below. The flow regime in the first region is said to be laminar flow characterized by smooth streamlines and highly ordered motion, and turbulent flow in the second region where it is characterized by velocity fluctuations and highly disordered motion. The transition from laminar to turbulent flow does not occur abruptly, rather it occurs over some region in which it fluctuates between the laminar and turbulent transitions before it fully becomes turbulent. 7. Methodology. The main software used in this project are the computer-aided software, namely Kasha for designing and ANSYS software for computational fluid dynamics prospect. All the relevant parameters are set according to the given limitation. Next, modeling in Kasha software using a type of MPV model as a reference. 3 different types of MPV model need to be figured using Kasha software, one without spoiler named MPV, with spoiler 90 angle with 20 cm length and 8 cm in height, Proton's original OEM specification, named MPVs, and the last with enlarged spoiler which were designed much wider from the original OEM specifications 100 angle, 50 cm length and 8 cm in height, named MPVSS. Then, all these models must be exported to ANSYS software to operate the CFD stream for all the MPV model for analyzing. The CFD stream need to be observed attentively and all the relevant details, result, graph, and data must be documented for further discussion and analyzing usage. 8. Modeling. Firstly, a MPV type vehicle need to be chosen as a reference to be modeled in the software. In this project, a locally assembled brand, Proton Xora, are chosen as a reference and all the parameters 10 are obtained and stated as in figure 4 below. Where overall length, 4,592 mm. Width, 1,809 mm. Height, 1,691 mm. Wheelbase, 2,730 mm. As the above parameters obtained, now it is ready to model a simple structure of the vehicle with 3 different models in Kasha software. The scale of the modeling is set to be 1:10. The modeled structures are shown in the figure 5, figure 6, and figure 7 as below. 9. Analyzing in CFD software, ANSYS. ANSYS software is mainly used for analyzing the designed model with comprising simulation which enables any individual or organizations to efficiently analyze how the product or model operates and responses in virtual environment. Besides that, it is also known to simulate interactions and properties of elements such as vibration, physics, structural, computational fluid dynamic flow, and heat transfer for professionals such as engineers, researchers, and scientists. Furthermore, ANSYS software has the ability to determine and improve any anemic points and foreseeing probabilities of complications which are both possible with its 3-dimension simulation. Therefore, in order to operate this software, one must learn the fundamental principles and explore the software by himself. Detailed steps and procedures are provided in its tutorial packages. After all the MPV models were obtained from Kasha software, it must be imported to ANSYS software in order to operate the CFD simulation. All the parameters and variables are stated according to the limitation explained earlier. The design will be further analyzed and as the data interpreted, the result will be composed due to the analysis summarization. ANSYS simulation. There are 2 different methods in analyzing the aerodynamic CFD stream of a vehicle, which is either using conventional wind tunnel or the other one is by running the vehicle model in ANSYS simulation, which is this project based on. As the ANSYS user interface appears, the systems chosen were fluid flow, fluent, and thus the related parameters/process is shown as in table 1 below and the settings are same for all the 3 models. All the settings gained are referred from ANSYS tutorial 11. 11. Result in discussion. The simulation performed for all the 3 different models, MPV, MPVs, and MPVSS, and the related graphical results were relatively obtained. The relevant element/characteristic of the vehicle's aerodynamic is being tested, such as the contours of pressure, total pressure distribution, maximum velocity, and the turbulence kinetic energy. The tests are conducted for all the 3 models with various speeds as stated below, but the graphical simulation only shows results for velocity, v equals 40 m/s equals 144 km per hour, because spoiler performs/responses better at high speed 12. 12. Multi-purpose vehicle without spoiler, MPV. Below are the graphical results of the simulation on MPV model for velocity, v equals 40 m/s. The maximum pressure is 1152 pa, maximum velocity is 61 m/s, and the maximum turbulence kinetic energy is 192.44 m2/s2. Figure 11 reflects the turbulence which occurs exactly at the rear compartment of the MPV model, thus increasing drag. 13. Multi-purpose vehicle with spoiler, MPVS. Below are the graphics results of the simulation on MPV's model for velocity, v equals 40 m/s. The maximum pressure is 1285 pa, maximum velocity is 60.8 m/s, and the maximum turbulence kinetic energy is 200.65 m2/s2. On figure 15, the turbulence occurs further from the rear compartment due to the spoiler of the MPV's model, thus decreasing drag compared to the MPV model. 14. Multi-purpose vehicle with restructured spoiler, MPVSS. Below are the graphics results of the simulation on MPVSS model with enlarged restructured spoiler of 100 degrees angle, 50 cm length and 8 cm height, with velocity, v equals 40 m/s. The maximum pressure is 1155 pa, maximum velocity is 62.8 m/s, and the maximum turbulence kinetic energy is 187.37 m2/s2. On figure 19, the turbulence dissipates even further from the rear compartment due to the structured spoiler of the MPVSS model, thus decreasing more drag and unable to travel faster compared to both the MPV and MPV's model. Graphical analysis. From the graphical analysis result above, figure 8, 9, 12, 13, 16 and 17 dictates the contours of static pressure on the vehicle model's body and symmetry. The stagnation point can be observed clearly at the front area of the vehicle model where the red-colored contour happens to be high-pressured region. When flow reaches at the rear end due to formation of wakes and turbulence and free stream flow, the pressure drops and the vehicle experience a net backward force. The total pressure for the 3 cases of vehicle model are obtained and the MPV's model shows the higher amount of pressure compared to the other 2 models. Figure 10, 14, and 18 shows the velocity contours on symmetry wall. The small red area shows the velocity has increased to maintain continuity and the blue contours appears to be a low velocity region. The velocity flow drops at the frontal area of the models due to some sharp edges/curves and it suddenly increased to the red color contour at top of the models. It shows the separation of flow on that region. As the flow continues on top of the models, wake occurs at the rear section of all the 3 models but fewer wakes obtained on the MPVSS model resulting in minimum pressure drag. This indicates that the MPVSS experience less drag force and able to travel/accelerate faster compared to MPV and MPV's model. Figure 11, 15, and 19 shows the contours of turbulence kinetic energy. For all the cases, the turbulence starts at the front top section of the models due to the sharp edges of the model's front windshield. From the existence of the rear spoiler, the turbulence flow can be dissipated further from the rear compartment of the vehicle model and allowing the weight to take effect. This can greatly reduce pressure drag but doesn't have much effect on the lift force. The MPVSS model experience lower turbulence kinetic energy compared to the MPV and MPV's model. Accordingly, it is evident that a spoiler really acts as a drag reduction device to reduce drag force even on a multi-purpose vehicle. 14. Model comparison. Below are the data and results retrieved from the ANSYS simulation, and in order to differentiate, tables and graphs are organized for better justification. The drag force and lift force obtained were auto-calculated from the analysis and demonstrates the same value using manual formula. Calculation. All the related data, results, table, and graph are as shown as below. For all the three model, MPV, MPVs, and MPVSS, simulation are analyzed using various speed, which is at 10 m/s, 36 km per hour, 20 m/s, 72 km per hour, 30 m/s, 108 km per hour, and 40 m/s, 144 km per hour, in order to obtain all the relevant elements such as the drag force, drag coefficient, lift force and lift coefficient. Besides that, this method is important to analyze at which speed the rear spoiler of the vehicle model can really performs. The sample calculation to obtain drag force, FD, and lift force, FL, for model MPV based on the obtained drag and lift coefficient from simulation results at velocity, V equals 40 m/s are shown as below, and for the rest are calculated automatically from the simulation, and the relevant graph are plotted below as well. In distinction to the complete table and graph obtained from the analysis result for all the three models, it is evident that the model MPVSS reduces drag force greater compared to the both models respectively. From the illustrated table above, table 2, 3, 4, and 5, it clarifies that the spoiler only responses on a vehicle at high speed is it only reducing drag force and drag coefficient beginning from 20 m/s and up to 40 m/s. Thus, the higher a vehicle's speed, the greater it reduces the drag for model MPVSS. Consequently, the lift force and lift coefficient for all the three models remains more or less the same at various speeds according to the table. Even in the graph obtained above, figure 20, 21, 22, and 23, the MPVSS model shows that both the drag force and drag coefficient are reduced greatly compared to MPV and MPVs, but nothing changes much on lift force and lift coefficient for all the vehicle models. Additionally, the drag force value can be used to calculate the fuel consumption 13 by using the formula of fuel economy/consumption as shown in figure 24 below. The value of fuel consumption for all the three cases of the vehicle model are obtained and clearly shows that with reduced drag force, fuel consumption of a vehicle can also be greatly reduced per 100 km, and thus spoiler can even functions as an alternate fuel-saving kit at high-speed cruising. Therefore, the structured spoiler on a multi-purpose vehicle, MPVSS, is the best model among MPV and MPVSS in terms of reducing the drag force, drag coefficient, and ultimately reducing fuel consumption at high-speed cruising. 15. Conclusion. In conclusion, based on the result attained from the simulation analysis, both the conceptual and theoretical aspects of the aerodynamic characteristic on the vehicle model are well acquainted. The spoiler unit on a multi-purpose vehicle does not act just as a cosmetic purpose or for sportier looks only, nevertheless it legitimately performs at high-speed cruising, reducing the drag force on the vehicle, thus increasing overall vehicle's performance. Therefore, it also evident as the multi-purpose vehicle with structured rear spoiler, MPVSS, travels at high speed eventually saves fuel consumption per 100 km compared to multi-purpose vehicle with rear spoiler/original full specification OEM, MPVs, and multi-purpose vehicle without rear spoiler, MPV. It also undeniable that with larger spoiler mounted at the rear compartment of the vehicle, the more it reduces drag force and increases the vehicle's performances. This can be seen as even though the MPVs model does reduces drag in a smaller margin compared to MPV model, but the superior MPVSS model can greatly reduces both the drag force and drag coefficient compared to MPV model. Besides that, the result also shows that there is nothing much changes on the lift force. This is due to the weight of the car itself, with 1,422 kilograms, and since multi-purpose vehicles are normally heavy, the lift force cannot be reduced much even with mounted rear spoiler, and thus the lift force on all the three models of the vehicle remains more or less the same. In conjunction with the analysis and results obtained, the objectives of this project are very well achieved, since the analysis results are well associated with the multi-purpose vehicle's rear spoiler's characteristic aligned with the theoretical and conceptual approach of a vehicle aerodynamics. 16. Recommendation. As for the recommendation in future studies, the vehicle model must be modeled entirely by considering the wheel, side mirrors and other element on the vehicle to construct better and precise readings/results. It also can be simulated using other properties such as K-omega model, RNGK, epsilon model and other CFD model to observe and differentiate the results on the aerodynamic characteristics of the rear spoiler. During the meshing part of the vehicle model, other properties may be considered and revised such as the relevance center, smoothing and transition to gain a better mesh of the vehicle model. The iteration number of the simulation on analyzing the vehicle model might be also increased to 1000 iterations or above if possible, to gain an accurate readings and better resolution of the vehicle's aerodynamics. Lastly, the experiment on analyzing the aerodynamics of a rear spoiler on a multi-purpose vehicle for future studies can also be held in the real-time wind tunnel model and compare the result obtained with the result by simulation analysis. This can improve the accuracy of the parameters and results of the aerodynamics characteristic of the rear spoiler on a multi-purpose vehicle. Besides that, there are other types of rear spoilers or drag reduction devices that can be installed and analyzed in order to study, experiment and analyze the additional decreasing the value of drag coefficient and aerodynamic drag force on a multi-purpose vehicle such as the wing type, diffuser type and even vortex generators.